we, okay, please go away. It says 30 seconds. Oh my good God. Got it. It's not working. Oh, it worked. It's okay. No, so once we got this, now there are other ways of doing this. The idea state that his model for intelligence is not a very good idea. We know that there's more to intelligence than a single factor. But then these days, we use this to explain all kinds of other things, psychometrics. You can have a person's psychology, and the psychology of a person's psychological responses can be explained in terms of a small number of factors. So here you had an intelligence factor, and G was the intelligence factor. A is what was called the loading. How much would be the typical score of a person of unit intelligence, G? And then, every person had their own G. So you can use the same thing for psychology, right? Psychometrics. A person's psychological responses to a variety of different things are explained by a bunch of different factors. Or educational testing. A person's broad knowledge in a variety of subjects can be explained through a small number of factors. Or data science, or your quiz course. So now that we have some way of defining this, I can try to understand. I can try to analyze you guys. And how would I analyze you guys? I analyze your quiz score. So D here is your is every person's quiz score. And we've had how many quizzes so far? Can you say it aloud? 10 quizzes, right? And so every person has a vector of 10 scores. And now Q1 through Q10. What do your quiz scores depend on? What is the course actually testing you? What are the quizzes testing you? Yeah.
Your ability to go back and read through the lecture slides.
Is that what it is? What are we really testing? So there are two primary things that we're trying to teach you in the course. One is, pretty much everything is dependent on your linear algebra, your facility with linear algebra. The other is your ability to understand probability and statistics, right? So there are two different factors that would decide your quiz course, which means that I could say that I have one vector, and this is what you would get. These are the portion of your scores that are attributable. I mean, each quiz invokes algebra and probability to different degrees. And so you're going to have, this is the algebra component of each of the quizzes. And then you'd have another one, which is your probability component of each of the quizzes. And so then this one over here, A and P, these are how good you are at algebra and probability respectively. So this would kind of explain your quiz score. But is that all? No, there's more to it, right? And that has to do with a second term where each quiz is individually more difficult or less difficult. A quiz has its own innate difficulty. And based on that difficulty and based on your own ability, you're going to score along that difficulty difficulty spread. And the difficulty of this quiz has nothing to do with the difficulty of this quiz. I just design each of these quizzes independently, right? On the other hand, if you're good at linear algebra, you're good at, on the linear algebra component of every one of the quizzes. And so here is a nice way of me trying to explain your quiz scores and trying to be based on the quiz scores, trying to judge how good you are at these two basic concepts that we have been trying to present to you guys. And then I could generate a two-dimensional plot, make each of your person on this plot, which is what Manohar here is doing as we speak. So when you're done, you will be a point on a two-dimensional chart. And it would explain give you some kind of an explanation. So this is factor analysis. The D over there, this here in the quiz scores, these are your data. This are what we call the loadings. Don't ask me why they're called loadings. These are your factors, right? Now, if I were to design the terminology, I would say this is my linear algebra factor. This is my probability factor. These are your individual abilities on these two aspects, but then they're differently termed. Those are called loadings. These are called factors, and then this is the additional independent variable, which is independent of the quantifies something that's local to each of the quizzes, each of the data instances in our case. So how exactly do we model this thing? You come up with a model of this kind, right? And so if I give you a bunch of data, what is the task? The task is for us, if I give you everybody's quiz scores, our task is going to be figuring out what these loadings are, because no one's actually sitting down and saying, here's how much of this quiz comes from linear algebra. Here's how much of it comes from probability. We don't, right? We're going to have to figure this out automatically. And then how to compute this term for every person, and then how to compute the residue for each person, right? So we're going to have to come up with the math for this. That makes sense to everybody? So this is standard factor analysis. But then once you look at it this way, you realize that this is actually very glorified principal component analysis, but in an interesting kind of way. And so before I continue, I'm going to present a few simple ideas. First, if I give you a two-dimensional Gaussian variable, so x and y, or x1 and y, x2, and then if they're both jointly Gaussian, then the overall distribution is going to be some kind of a bell-shaped curve, right? It could be elongated in different directions. It could be oriented. It doesn't really matter. And so if I looked at the Gaussian from the top, you're going to get something like this. This is 2 dimensions, and maybe your equal probability contours look like that. Now, if I give you, so let's call this, what am I calling the variables? X and y. So this is x and this is y. So now suppose I tell you that x is this particular value, x1, right? What does it tell me about y? It's like saying I'm slicing this probability distribution at x1, because x1 has been given, right? And so the probability distribution itself is going to be whatever is out here, as shown by the figure to the top right. If I slice it at x1, the result is also always going to be a bell-shaped curve, because this is a Gaussian. And now, if I ask you, when x equals x1, what is the most probable value of y? What would it be? Over here. Anyone, this is going to be a Gaussian, right? You're going to pick the value of y at which the Gaussian peaks, correct? And the Gaussian is symmetric. So if the Gaussian is symmetric, it means that the value of the Gaussian here is the same as the value of the Gaussian here. So where is the maximum peak going to be? Right in the middle, out here. Not here, but slightly above it, right? I can do this for every x. If this were x, what is the most likely value of y? It's going to be the midpoint of these two guys, maybe over here, right? And so when I plot this line, it's going to be something of this kind. At each value of x, I can tell you what the most likely value of y is going to be, and that most likely value of y is going to follow a line. Okay. And here, if the value of x is the mean of x, then the most likely value of y is simply going to be the overall mean of y, right? So we know this line goes through mu x, mu y. And so what is the equation of a line that goes through this point mu x, mu y? What is it going to be? Anybody? 4th grade algebra, geometry. Come on, you know this. What's it going to be? Dareen, what's it going to be? You guys at the back, how would you go about it?
Just find a second point on that line.
So here is the thing, right? You know what the equation of the line is going to be. For every offset from here, if I offset by some delta x from mu x, right? Then I'm going to have a corresponding offset delta y from mu y, right? That's what we know. And so I know it goes, so the equation of the line is going to be x minus mu x, y minus mu y is going to be some slope times x minus mu x. As you move away from x by any small amount, you're going to move away from the from mu y by some amount, and how much you move away by is going to be the slope of the line, right? So this is your standard equation. So all I need to know, if I give you mu x and mu y, what is the slope in this case? Now I have the Gaussian, right? What did we say the correlation between x and y was when we were speaking about correlations a few classes ago? If I gave you a correlation value cxy or cyx, what did this tell us? You remember?
How much y explained x?
How much y tracks x? That's what we said. If the correlation was 1, then for every unit step in x, there was a unit step in y. Do you remember this, right? So that clearly means that the slope has got to be cyx, right? But is it enough to say cyx, or should I make x unit invariant? If I report x in centimeters instead of inches, this would change the value, right? You want to make it in unit invariant. How did we make it unit invariant? We whitened it. How?
Negative square root to negative square root.
So negative square root of x. So we can just say y minus mu y is going to be here cyx. This is the cxx minus half. So I multiply the negative square root of x over here because I whitened this. But then this x minus mu x is also going to be multiplied by cxx raised to minus half. So both of these guys are normalized. So I can multiply these two guys and just call it cxx raised to minus 1. That makes sense to everybody? Based on the correlations, right? And so that's what we've got. The equation of the line over here is, if you look at this line here, at any y, so this cross section is also going to be Gaussian. The peak of the cross section is going to be the mean. And that's simply going to be at any y, you say, thank you. So at any x, just following this little equation, we're going to say over here, the new move. So this guy is going to be the mean of y at the new x, right? So mu y hat equals mu y plus cyx inverse cyx cxx inverse x minus mu x. So this is basically the most probable value of y at the given x, and it's going to fall on the line. The equation makes sense to you guys? How I got it, yeah.
Is there a reason why we don't whiten out y?
You're predicting y, right? That's about it. So I'm trying to predict y from x. Whitening it is not going to help you anything, right? Now, that's one step. So the other thing, so the best guess for y when x is not known is mu y, right? And then for any shift x from mu x, x minus mu x, the corresponding shift and the mean of y is going to be multiplying x minus mu x by the slope, which is simply cxx inverse times cyx times cxx inverse. Because cyx tells you how much y tracks x, but you want to whiten, right? And so this explains the mean of, again, notice that we're looking at the distribution of y given x. It's going to be a Gaussian, and the mean is at this point, okay? What about the variance? So here's the other thing. If I've got a Gaussian distribution, if I don't tell you what x is, then y can lie anywhere in this range. So y has a large variance, right? But if I tell you x, if I say x is out here, suddenly y is restricted. So will knowing x reduce the variance of y or keep it unchanged? It must reduce it, right? How much will it reduce it by? So you're going to find that if you don't know x, the variance of x is something like c by y, right? But then if you know x, this is going to be reducing by this amount. And what is that amount? If you go from y to x, wait a minute, and then go back from x to y. So if I start at any y, predict x from it, and then go back and predict y again from that predicted x. That's the predictable portion of y, right? And so this guy here is how much of y I have predicted. I have predicted x from y. This was required for whitening. And then I've gone back and predicted y from x again. And this is how much the uncertainty has reduced because I know x. And so this correction over here, the uncertainty reduces, right? This uncertainty in y when x is not known. And this is the shrinkage in the uncertainty in y from knowing x. And observe that the shrinkage in the uncertainty in y doesn't depend on the actual value of x because it's a Gaussian. All you know is that once I know x, my uncertainty in y is going to decrease. And how much will it decrease by? If I predict x from y and then predict y back again from x, it's going to keep coming back at the same point, right? So that variation is how much it's going to be reducing things by. That makes sense? So let's note these two things down. This is for reference. If x comma y is Gaussian, then P of y given x is also a Gaussian, where the mean is mu y plus cyx, cxx inverse x minus mu x, and the variance is going to be the variance of y minus cyx, cxx inverse cxy. I can do this blindly because it just makes sense to me. Okay, so is everybody good with me so far? Where these things came from? Because we're going to encounter them again. Okay, so knowing x modifies the mean of y, and shrinks its variance because you have added some knowledge. Now I'm going to add a second equation. So let's keep track of this one first. A second exercise where I'm telling you that I have some variable x. Falling behind, but yeah. I have some variable s. And I say O equals AS plus epsilon. Okay. And I'm also telling you that S over here comes from a Gaussian with variance mu s and a mean mu s and variance theta s. And epsilon over here is some independent noise. S is independent, epsilon is independent of s. And it has variance mu epsilon and a mean mu epsilon and variance theta epsilon. Then what is the expected value of O over here? What is the distribution of O? S is Gaussian, epsilon is Gaussian. So I have scaled the Gaussian by a matrix A, so that remains Gaussian. So when I add the two, what is the sum of two Gaussian random variables? What is the distribution? If I take two Gaussian random variables and sum them, what is the distribution? If I add two Gaussians, the result is always going to be Gaussian, right? So this comes back, if you go back to our independent component analysis lecture, I told you, if I keep adding more and more variables, eventually things become Gaussian because the Gaussian is the most random of all possible distributions, which means that if I'm adding two Gaussians, there's nowhere for it to go. The result is still Gaussian, yeah.
Does that like have to do with the central limit theorem?
This is provable, but the central limit theorem is this is one of the consequences of the central limit theorem, but it's independently provable, right? So this means that O is Gaussian, right? What is the variance of O? Over here. What is the mean of O? I can just say the expected value of O is going to be the expected value of A times S plus epsilon, right? Which is simply going to be A times the expected value of S plus the expected value of epsilon, which is A times mu S plus mu epsilon. It's just going to come out to be just that, right? Simply, I plug it in. What is the variance? So I can add this to my little nuggets of knowledge. I can say O equals AS plus epsilon implies, this is Gaussian, this is Gaussian, implies P of O is going to be a Gaussian, and the mean is A times mu S plus mu epsilon. And what will the variance be? Right, so this is basically what the mean is. What is the variance of S over here? If I add two independent random variables, what happens to their variances? I add two independent random variables, their variances will, it's going to be the addition of their variances. Yeah, you can look at this, right? So the variance of O is simply going to be O minus mu times O minus mu transpose, right? And then we say O is going, so if you just work it out, this is going to be, this is a standard statistical reality. If I take two independent random variables X and Y, right? Let's say if O equals X plus Y, X and Y independent. Implies variance of O equals variance of X plus variance of Y. This is just a truth. Now it's easily proved. I'm not going to spend any time proving it. You just have to believe this, okay? So in this case, now given here, second, if I have, O equals some A times S, what is the variance of O? If I know the variance of S, what would it be?
A variance of O A transpose.
Implies the variance of O is going to be A times theta S A transpose. Because it's just a multiplier, right? Nothing really changed. And so I can just add this as A times theta S A transpose, which is the variance of AS plus theta epsilon. Did this make sense to you guys? Over here. Straightforward, nothing particularly complicated, right? Everybody with me? Okay. And secondly, so finally, I'm going to add something. So are either of the two derivations on top unclear, or did they make sense? The first one is the probability distribution of Y given X is a Gaussian. The mean is going to lie along the line. The variance is going to shrink. The second is the probability distribution of O is simply a Gaussian where the mean is O times mu S plus mu epsilon. And the variance is A theta S A transpose times plus theta epsilon, right? Now, here's the third thing. This is a little more. I have a proof over here. It just shows this, okay? Another thing, if I say O equals A times S plus epsilon, right? Same thing. Without actually going into the proof. If I say O equals A times S plus epsilon, right? What is the cross correlation between O and S in this case? What would the cross correlation between O and S be? Anyone?
A times the variance of S.
So the cross correlation between O and S is simply going to be A times theta S. Easy to show, right? And that's basically what, I don't know why these things have moved on my screen. They shouldn't have. But if you just work out the arithmetic, this just follows. Okay. So just using this, I can just say the cross correlation between O and S equals A times theta S. The cross correlation between S and O is going to be theta S times A transpose. That's the transpose. Okay. I'm adding a bunch of different things. Again, is any of this controversial so far? You guys, anybody find any of this controversial? No, okay. And now here is the crazy thing now. If I say O equals AS plus epsilon, what is the joint distribution of A and S? S is Gaussian, epsilon is Gaussian, O is Gaussian. So the joint distribution of A and S has got to be Gaussian, right? And if the joint distribution is Gaussian, then the mean is simply going to be the vector of the mean of O and the mean of S. And we know the mean of O is simply A mu S plus mu epsilon. The mean of S is mu S. So the mean is very, very simple. Okay. And then secondly, what is the covariance matrix of Z, which is the joint of O and S? That is simply going to be this matrix here. This is theta O, theta OS, theta SO, theta S, correct? Everybody with me in this? And so that's, I can expand it out. I know theta O is this guy, A theta S, A transpose, plus theta epsilon. We just saw that theta OS is A times theta S. Theta SO is theta S times A transpose. And the bottom right is simply the variance of S inverse itself. So is anything controversial about this statement? Over here. Just going to add this. If I say O equals AS plus epsilon, implies P of O comma S, which is the joint of O, is a Gaussian, which is, what do we have here? That is A mu S plus mu epsilon within a mu S. This is the mean, and the covariance is A transpose A theta S A transpose and theta S. Again, anything controversial about this? No. We've sort of built through a whole bunch of equations. None of them is particularly complicated. And is there any reason for you to disbelieve any of this? What we've just done is gone through about 30 years of research in about 10 minutes. Because something crazy happened right after this. How do I move this all the way up? Can you guys see the stuff on top? Okay. And so then here's the final bit. If I say A equals, I'll write this here because I need this board. If I say O equals A times S plus epsilon, and I'm telling you that S is Gaussian and epsilon is Gaussian, I ask you, what is the probability distribution of S given O? So the observation O is obtained as the sum of two Gaussian random variables. One of them has been translated by A, the other is sum by, it's also a Gaussian random variable, right? How would I derive this? It turns out that if you go about working or working through the arithmetic to derive this conditional distribution, you're going to write pages and pages, and you're going to end up with the wrong answer more often than not. But then guess what? The answer is up there. I'm hidden up there. Why? Because look at the bottom. I know that the joint distribution of O and S is a Gaussian. And I know the mean and the variance of that Gaussian, right? And so I know that when I have two variables which are Gaussian, the conditional distribution of one variable conditioned on the other is also Gaussian, right? And specifically, this is going to be a Gaussian where using the very first thing on top, this is going to be mu s plus this is theta SO times theta OO inverse times O minus mu O. That's just using the formula on top. Right, and the variance is going to be theta SS minus theta SO theta O inverse theta OS. So I'm just using the formula in white on top, except I replaced X and Y by O and S over here, right? And then I can go to those pink equations. And I know what this guy is. Theta SO is simply A times theta S, right? Is that what it is? Theta SO is theta SA transpose. So, yeah. You can basically read each of these guys off. So theta O is A, theta S, A transpose plus theta epsilon. This is what we've got also. I plugged all of those in. And so if I plug these terms in right here, it turns out that when I try to compute the conditional probability distribution of S given O, just putting things into place, I can end up with this completely crazy looking formula over here, which looks ugly. This looks particularly ugly. And if we try to derive it all the way from scratch, it's going to be very hard. But just following those steps one at a time is going to end up giving you this very pretty formula, which is that, yeah, P of S given O is a Gaussian with mean whatever else. Why does all of this matter? We will see in a bit if I can actually get all the way to the end of class. Plus, I just add this, right? This is theta SO times theta O inverse O minus mu O. And the variance is theta S minus theta SO, theta O inverse theta OS, where theta O and theta S are defined up there. Okay, so I know this was a bit confusing, but anyway, did this make sense to you guys? One step at a time, right? You don't necessarily have to remember the formulae, but you saw how the formulae, there was nothing particularly complex about any given formula. They just followed one after the other. Did they? No. Shravan, did they? Yes, okay. All right. So you guys, Verity, you were kind of late.
Yeah, I'm trying to follow.
Okay, so just believe all the stuff on top, okay? And then I'm going to change topics. But first, there's a poll. You can use your phone. Yeah. Is that a question? No. Very nice. We actually have a factor analysis of your quiz scores. Okay, first statement, true or false? Second one, true or false? True, also true, right? Okay. Then, so far so good. I'm going to, the other thing that I wanted to remind you of, that was just a bunch of linear algebra just to warm you up and make sure that you guys are asleep. And now the second one is EM. What was the basic idea behind expectation maximization? Anybody remember? You had incomplete data, right? So what did we do? But how did we do it when you had incomplete data? Anyone remember? Yes.
Like samples from the posterior.
We completed the data, right? And we completed the data by drawing the missing components from the posterior distribution of the missing components, conditioned on what was observed. And now you had the completed data, and then you could go back and re-estimate your parameters. But then when you re-estimate it, then the posteriors would change, so you can keep iterating this thing. Now, instead of just taking a sampling from the posterior, you can take an expectation over the posterior distribution. That works as well, right? So we can actually consider every possible value for the missing components with weight that's proportional to their posterior probability, or you can just sample the posterior probability to complete the data. And then once you completed the data, you can re-estimate the model. This was the basic idea of EM, right? So hang on to that, and then we're going to change gears. Questions? I know it was all very confusing. So questions. Good morning. Right? Questions? It doesn't yet. They're two independent concepts. Okay. We're going to draw on all of these. I just threw a bunch of things at you, and then I'm going to be talking about factor analysis. All right. So here's where. First, we're going to talk about principal component analysis because I want to warm you up with something that you're familiar with. What was principal component analysis? We wanted to find the principal subspace such that when all vectors are approximated as lying on that subspace, then the total projection distance was minimized, right? So assuming zero mean data. And so what we were doing was minimizing the squared length of those lines. This you remember, I assume, right? And so basically what we did was basically find the principal subspace such that when all the vectors are approximated as lying on that subspace, the error is minimized. So you basically scanned through all possible subspaces and computed the total squared length of all of the projection errors until you found the one subspace where this total projection error was minimized. And this was your principal subspace. Everybody remember this? Easy, right? And so how did we do this? For any given W, which could be a single, a bunch of bases, we wanted to minimize the L2 errors. And so what we did was we found out how much the error would be if you projected the data onto that W. And then this error actually has a nice formula using Pythagoras theorem. And so this one was what we got. That's the error. We sum this error over all of your training data. Oh my God, what has happened to my display? Exciting, okay? We sum this error over the entire training data. And then when we solve for it, guys, this is not what is supposed to have happened. My slides are destroyed. This happens when you use Dropbox. You have to assume that you're seeing the right thing, okay? Because you've looked at this before. You ended up with an eigenvalue equation that we solved, right? Is this the only way to solve principal component analysis, or can we do something else? So here's what we can do, right? There's an iterative solution. And the iterative solution is this. First, what we were really doing, we had this data X, our data matrix X, and we were trying to, did I call that X over there? Yeah, and we were trying to come up with a bunch of bases. And these were the weights, the Z were the weights, the Z were the coordinates in this new space. And we wanted to find the bases W and the coordinates Z such that the error between these two is minimized, right? So we were trying to minimize X minus WZ whole squared. Now, in terms of WZ, is this a quadratic? Is this convex? Is this error convex? So how many solutions will it have?
One.
It's going to have a unique solution, right? So that means that it doesn't matter how I go about it, as far as the product WZ is concerned. Any kind of iterative solution which keeps reducing this error is going to give me the same solution, right? It's going to give me the same subspace. So let's say I give you Z. Suppose I give you Z and say find W. How would you do it?
You use like gradient descent.
Do you need to use gradient descent over here?
Pseudo inverse.
Pseudo inverse, right? If I give you Z, then W equals X pseudo inverse of Z, correct? Does this reduce the error? You found the small lowest error solution, lowest squared error solution when I use the pseudo inverse, right? And if I give you W, can I estimate Z? How would I do this? If I give you W, can I estimate Z?
That'd be pseudo inverse X.
Z is going to be W pseudo inverse X. Both of these are possible, right? And so that gives you an iterative solution. I can fix Z, I can estimate W, I can fix W, I can estimate Z. If I keep flipping back and forth, every single step is going to be minimizing the error in terms of WZ. And eventually it will converge. And it's going to give me the correct solution. It's going to give me the correct subspace. So you don't even have to solve the eigen decomposition. This would also give you a solution. That makes sense to everybody? Right, and so this is basically what we are doing. I could be initializing my subspace W. When I initialize my subspace W and find the Z, what am I really doing? I'm finding the perpendicular drop on the Z. So you can think of this as there being some kind of a ball. You can think of Z, you can think of W as a subspace on which you have balls which can roll. You know, they're magnetized, they stuck to the surface, stick to the surface. And then when I fix Z, and then if I tied a string, so think of it this way. So let's say all of these are balls on my surface, right? And if I tied a string from my data point to its corresponding ball, every string is elastic. Where would it move the ball? It's going to move the ball till the string is as short as it can possibly be, correct? So every data point is going to end up exactly beneath the ball, right? That makes sense? I mean, every ball is going to be exactly beneath the data point. So that's what estimating Z given W means, right? But then I do the next thing. I fix Z. Fixing Z is basically the same as saying now I'm fixing the coordinates on the point, which is to say I'm no longer allowing this ball to move on the surface. I'm sort of sticking it there. I'm stapling it to that point, okay? Then after stapling it to that point, what I will do is allow the surface to rotate. And again, the intention is to reduce the total length, the total tension in the strings. So now the strings will no longer all be perpendicular to the surface, but every string is going to try to shorten itself. The longer strings are going to work harder, the shorter strings are going to work less hard, and eventually the whole place will tilt to the whole surface will tilt to a new position. So this is re-estimating W given Z, right? Now I fix W and I say I let the red balls move. And they're all every ball is going to move to a new position where the strings are as short as possible. At each step, the overall length of the strings is reducing, right? Now I can fix the balls again and let W rotate, and it's going to give me something else. Then I can release the balls and I can let them slide, and it's going to come to a new point. So every time I'm doing this, I'm going through a two-step process. I'm fixing the W and letting the Z change, then I'm fixing the Z and letting the W change. If I keep doing this, eventually it's going to end up at a place where the strings are as short as they can be, and neither moving W nor moving the places where the projections is going to reduce the error. So I tried to come up with an animation for this. MATLAB barfed on me. So if somebody wants to help me come up with a better animation, you're welcome, but this sort of conveys the idea. Step by step, this is basically what's happening, right? So after a while, things just stop moving, okay? Anyway, so there are a couple of things over here. This is only guaranteed to be optimal in terms of WZ. It doesn't say anything about W particularly. So I could be multiplying W by some A. I could be multiplying Z by some A inverse, and I'm still going to get the same solution, right? So in other words, if I look at the data points over here, this is in my, if I'm just saying W equals XZ plus Z equals W plus X, I'm not imposing any constraints on W or Z. It's just trying to find an overall solution. So there's no requirement that W and Z must, the bases in W must be orthogonal to one another. So I can get different sets of bases, and by changing the bases, I would get different coordinates, and all of them would still give me the same subspace. So there's a lot of variation over here. So the solution is not unique because WZ equals WA times A inverse Z, right? So you could end up with these as my bases and these as my coordinates. And that's where your standard formulation for PCA came in. Although you have all of these possibilities, you want a unique answer. And so for PCA, one of the two things we did was to say that we want the vectors in W to be orthogonal to one another. And the moment you say the vectors in W must be orthogonal to one another, you get only one of the many possible solutions, and you get a unique solution. But there's another way of saying that I want my vectors to be, I want to get a unique solution. And there, instead of imposing constraints on W, I can impose constraints on Z. And the constraint I will impose on Z, because I get a different Z vector for every data instance, right? I can say the constraint I impose on Z is that the collection of Z vectors must have a standard Gaussian distribution. And so I can say the variance of Z to be unity or the identity matrix. And if I do that, that is also going to give me a unique solution. And the two solutions are, the bases I will get in the two cases are going to be different, but they'll have the same subspace, okay? So this is the one that's of interest to us when we're talking of factor analysis. What exactly is happening when I'm constraining the variance of Z to be unity or the identity matrix? This is what's happening. We go back to our original problem. I had a collection of data points. I was trying to find the principal subspace, but when I find the principal subspace, I have to do two things. I have to find bases on the principal subspace because the bases define the subspace. And then I have to find the coordinate of every point in this subspace in terms of these bases. So I need the Z and I need the W, right? And we saw from here that if Z was given, that's enough to estimate W. Corresponding to every data point, there's a Z. So if Z was given, that's enough to estimate W. And so we are saying we're missing the Z, the coordinates for each data point. And if the coordinates were available, the solution is easy. So here's what we did. We initialized the plane, use that plane to fill up the Z values, then use those Z values to go back and re-estimate the plane, then use the plane to go back and re-estimate the Z values, and we kept going back and forth, right? So what are we doing over here? We have some missing values, namely the Z's, and at each point, we are estimating the missing values in terms of our current estimate of the model, then using the Z's to go back and re-estimate the model and repeat the process, right? What does this look like? This is just EM, right? So principal component analysis is actually just performing expectation maximization. Did that make sense to you guys, right? So this looks like EM. In fact, it's just exactly EM. And so anytime I speak of EM, we always speak of EM in terms of probability distributions, right? Where is the probability distribution over here? I didn't actually explicitly give you a probability distribution, but there must have been because this is an EM solution, right? So what is the probability distribution and what is the generative model and what distribution is it encoding? It turns out the underlying assumption for PCA is that the data has a Gaussian distribution. And so let's say we started off by assuming that the Z's are Gaussian, right? So if I assume the Z's are Gaussian, okay, there's a problem. You have the plot? Hmm. Students, huh? There's an outlier here. Very nice. Very nice. Okay, we'll show you some plots once we are done, having analyzed your quiz course. First statement, true or false? Generative models require large amount of data to train properly. They do, right? Otherwise, it's going to be noisy, right? The amount of training data is smaller if the maximum likelihood estimate has a closed form formula. Absolutely nothing to do with the nature of the formula. That has more to do with distribution, right? EM can be used to learn the parameters of a generative model for which closed form ML solutions are not available. Very true, right? PCA can be implemented in an iterative way by alternately estimating the principal components and the coordinates of the data vectors. So just the last two are true, right? It depends on the model. Okay. The simple models don't require very much. Okay. So here's the generative story behind PCA. So PCA has a generative story. It says that Z is a standard Gaussian, right? So the PCA says that my data have a Gaussian distribution. There's this principal subspace. On the principal subspace, the data have a Gaussian distribution. So in order to generate a data point, I'm first taking a Gaussian step along the principal subspace, and then taking a Gaussian step 90 degrees to the principal subspace. Why 90 degrees? Because we're always looking at projections onto the principal subspace, right? And so PCA finds the plane and the characteristics of the Gaussian steps on this principal subspace. You can write the math out for this. I won't spend time on it. But basically, you're saying that I'm drawing Z from a standard Gaussian. I'm putting it through a linear transform A, which is going to give me this new point on the principal subspace. And then I'm adding some noise to it, which is at 90 degrees to the subspace, principal subspace. And that's going to give me my data point. So that's the generative story for PCA. And so the step on the principal subspace is Gaussian. The step 90 degrees to the principal subspace is also Gaussian. So the overall distribution is going to be Gaussian, right? And then just using all of the formulae that we just had over there, what PCA is actually doing is getting a maximum likelihood estimate for the bases of the subspace. It's also getting a maximum likelihood estimate for the variance of the error that's at 90 degrees to the subspace. That's basically what is happening with PCA. And so you can actually write the math out. Where is my trident? Over here. And it's going to give you a nice, it's going to give us the solutions that we are familiar with, right? We are saying that what happens, there's a different way of looking at it. Z is a standard Gaussian. So if Z is a standard Gaussian, it's like saying I have an isotropic circular distribution on this low-dimensional plane. What happens when I transform this low-dimensional plane through a transform? It gets stretched and rotated. And so this standard Gaussian becomes a skewed Gaussian in a higher dimensional space, on a low-dimensional plane, on the higher dimensional space, right? And so samples are drawn from this ellipsoidal distribution in the hyperplane, and the noise that's perpendicular to it is added. I can write out the mathematical formula for this. If I say Z is Gaussian, then the probability of AZ is going to be Gaussian with zero mean, and the variance is just AA transpose, right? Because the variance of Z is I. So the Gaussian distribution of X plus E, where E is the noise that is added, is simply going to be the same. It's a Gaussian with zero mean, and the variance is AA transpose plus the variance of the noise, right? And also, what is the probability distribution of X given Z? If I give you Z, then the only remaining variation is the noise. And so the probability distribution of X given Z is simply a Gaussian with mean AZ and variance T. Now we can you can write all of these out, right? So once I do this, if I have a bunch of data points, this is the one that's important, right? Why is this the case? Because if I give you Z, then this X hat is fixed. X hat is simply going to be AZ, right? And then I'm adding noise to it. So it's like saying I have the distribution for Z, but for the noise, and I'm shifting the mean of the distribution to AZ. That's it, because Z is given, right? And so once you do that, you can actually write the probability distribution for X. If you have a collection of data points, you can write out the log likelihood for each of the data instances. And you can, let's assume that you have, and trying to solve this in closed form is going to be impossible because, as always, it's got the log of the variance as AA transpose plus B. It's kind of ugly. It's not going to be solvable. But then I can go back and realize that there's missing information about the observation X. For each data point X, I don't know Z. I don't know what the Z that went into the transform was. So I can ask myself, what happens if I complete the data? If I give you the Z for every data instance, what would happen? And if I gave you the Z for every data instance, then instead of getting this ugly equation with AA transpose plus D and this determinant of AA transpose plus D in a square root in the denominator, I get something much simpler. What I get is this guy. I get P of X given Z because Z is given to you, which is just a simple Gaussian, right? And then if I give you the Z, I get a much simpler formula for the probability distribution, if I assume that I gave you the Z, right? And thereafter, I can perform my standard maximum likelihood estimate. And I'm going to end up with the solution which says that A equals X times Z plus, which is basically the formula I had on my board. The problem is we don't have Z. So what I can do is I can try to fill up Z. This is basically what we did. This was what PCA was doing, right? So the basic idea is, again, in the iterative EM solution for PCA, you recognize that if I had Z, the solution becomes simple. So you iteratively keep estimating Z and filling up the Z, and you're going to get the solution, okay? Now, here's a last poll before I jump off into factor analysis. I should have spent an hour on it, but I'm going to spend 15 minutes. The poll is not up. It's got to be up. All right, first question, true or false? And the second one, so what is the actual probability distribution that PCA models? It says the data are Gaussian on a plane with a little bit of Gaussian noise off the plane. So the overall distribution is assumed to be Gaussian, but very close to a hyperplane. That's the model of PCA, okay? So the two statements are true. But then this is where factor analysis comes in. PCA is making a very interesting assumption, a very simplifying assumption, which is that the error is always 90 degrees to the plane. That you're taking a Gaussian step on the plane, and then the noise you're adding is at 90 degrees to the plane. Where did that assumption come in? When we're doing the perpendicular projection onto the plane, right? But then if I think of it as a statistical model, where I generate some data and add some noise, does it make sense for me to assume that the noise is always going to be orthogonal to my data? Now think about, example of speech, right? As I speak, you can hear me, but there's some noise. If I stop speaking, and if you close your eyes and listen to all the sounds in the room, can you hear whispers? Don't you occasionally hear something that sounds speech-like? That's where ghosts come from, spooky stuff, right? The noise is not completely orthogonal to speech, right? If you look at a blank screen with just speckles on it, you will actually begin seeing patterns, you can see faces, you can see trees, you can see whatever it is you want to see. That's because the noise, again, it's faint, but it's not completely independent of the data that you're trying to estimate. The noise can look like the data. So which means that the assumption that the noise is orthogonal to the principal subspace is kind of inaccurate, right? So how can I change that? I can say that I'm transforming Z through a linear transform, and then now I'm adding noise. But now I'm no longer requiring that the noise must be orthogonal to the surface. The noise can be isotropic. And once you make this assumption, right, this noise is it's a full rank noise. The noise can be in any direction. And so then this noise variance is going to be a full rank diagonal matrix. Every component is independent of every other component. And that is going to be the new model. This is an upgrade on principal component analysis. Principal component analysis is very simplifying assumption that the noise is always orthogonal to the signal is no longer being made. And so here is what, but this causes a problem. And the problem is this, that in your standard PCA, if I gave you the subspace, right? And PCA, if I gave you the subspace, I said this is my subspace, and then I gave you this data point, then the location on the subspace from which this data point was obtained is uniquely specified. That location is exactly below the data point because we said that we are looking at perpendicular projections. The error is always at 90 degrees to the signal, right? Once I get rid of that, so corresponding to every X, there was a unique Z. Given X, Z was unique, right? But once I get rid of this assumption and I say that the noise can be in any direction, this assumption breaks down. Then we get all of these different possibilities for the signal from which the data was derived. And so the rest of the math stays the same, right? The probability distribution of X is simply a Gaussian with, mean. Should have been the mean. This guy over here, the mean is off, but it's going to be A times the mean of Z plus. Yeah. Its mean is 0 and the variance A transpose plus T. That's X semicolon, right? So the probability distribution of X is again specified. And this is factor analysis. A is the loading matrix. Z are the diagonal factors. Z are the factors, and D are the D is a diagonal matrix with the error, which goes back to Spearman's original model. This is the model that Spearman had when he was trying to explain things. And the only difference between this and PCA is that in PCA, the error is supposed to be perpendicular to the surface. Here, the error is allowed to be in any direction. But this little modification makes things much more complicated. So how much more complicated? Here's what happens, right? This is the model again. When I put Z through the transform A, I get the initial position on the subspace, X hat. So X hat is going to be AZ. So the probability distribution of X hat is simply the variance of Z was 1. So the variance of X hat is going to be AA transpose. The mean of Z was 0. So the mean of X hat is 0. Once I add noise to it, assuming the noise is 0 mean, I'm just adding the variance of the noise to the variance of X hat itself. So this is the probability distribution of data modeled by this. And if I give you Z as before, the probability of X given Z is just going to be a Gaussian with mean at AZ and the variance D. Nothing has changed as far as PCA is concerned. And like PCA, this is assuming that the data is a Gaussian distribution. It largely lies on some hyperplane with a little bit of fuzz off the hyperplane. The only difference from PCA is that the noise at any data point can be in any direction, right? And so how do we estimate it? Again, same thing, right? I can write out the probability distribution for each data point X. And then I can try to optimize it. And the same issue that I had with PCA is going to happen over here. Again, there's no closed form solution. Again, I can go back and note that if corresponding to each X I had the Z, the solution would be trivial. The problem really is that I don't have the Z for every X. So let me start off by assuming that I have the Z for every X. So if I have the Z for every X, then I no longer have to worry about the probability of X because Z is given. I only have to worry about the probability of X given Z. The moment I begin thinking of the probability of X given Z, then this ugly term we had over here, which was a sum of two terms inside the variance, the A, that goes away because once I give you Z, the only variance that remains is the variance of the noise itself. And so I just end up with a much simpler formulation for the log likelihood of the data if I give you Z. And then you can, and then you can just differentiate it and you get a nice closed form solution for the parameters of the model. So again, this is just going back to the whole EM setup, right? That if I gave you Z, there's a nice closed form solution. The problem is Z is missing. So given all of this and everything that we've seen so far, what would our solution be? Anyone? I've given you this, that if I had Z, I can get a closed form solution, but I don't have Z. So what would we do? Yeah, we're going to complete the data, right? And how do we complete the data? We just fill up Z, right? We're going to estimate Z. And how do we estimate Z?
Take it from the posterior distribution.
Take it from the posterior distribution of Z given X, right? Very simple. And so this is just a closed form solution. I won't go into the arithmetic, it's on the slides. But it's actually a very, very simple solution. And it actually turns out this looks a lot like pseudo inverse. So this guy over here looks like X times pseudo inverse of Z, right? I'm just writing it out. And this is the variance of D, the noise is the variance of X minus whatever is predicted from, how much ever of X is predicted from Z. So that's about it, right? It's all very easily explainable. The problem is I don't have Z. And so I want to complete the data by filling in the Z, and I can do it in one of two ways. I can think of every possible way of estimating Z, or of filling in the Z. So in the one case, I have a formula over here in terms of Z. And if I want to consider every possible way of every possible value of Z, then all I would do over here is take the expectation with respect to Z using the conditional distribution of Z given X. And so that's going to give me, let's skip that. Now, what is the conditional distribution of Z given X? For this, we have to go back to, you know that the joint probability of X and Z is Gaussian. Z is Gaussian, X is Gaussian. We go back to the formula we wrote way up there early in class. And that's going to give me the conditional distribution of X given Z. This is, the mean is going to be X minus the mean of X, which is 0. This is the inverse variance of X. And this is the cross correlation between Z and X, A transpose. That's about it, exactly as we had before. And this is the variance of Z by itself. And this is how much the variance of Z reduced because I've seen X. So same thing. And so we can just complete the data in every possible way. I have P of Z given X. I have a formula for it. And I can take an expectation with respect to this formula. And this is basically what, if you have the math, if you work the whole math out, it just looks like these are expectations, right? You can plug in the formula. The easier thing for me to do is to just sample from P of Z given X, and then just use the formula straight up. And that's going to give me factor analysis. So I'm kind of out of time. I should have spent a lot more time on the second half of the lecture, but I know I'm boring you guys. So I'll leave this, but just to make things interesting, maybe Manohar can show us what we've got from your quiz coach. You can. You have HDMI? Okay. Wait. How is it showing that? Was the HDMI not being used at all? What were you doing? This is magic. It's still showing the same thing. Aha, yeah. Wait. Came and it went. Shut my laptop, maybe that will happen. How did that